Hello again. Welcome back. Bioinformatics, another short lecture. This one's going to be just a few slides. They should be available on Google Drive already, and followed by a short little activity in Excel. So let's get started. I'm going to share my screen with you now to look at the slides. Okay, so we started off talking about multiple sequence alignments, why they're useful, why they're powerful, what they look like, and what defines a decent or acceptable multiple sequence alignment. Over the next 3 lectures, we're going to talk about 3 different approaches to generating multiple sequence alignments. And we'll go from simplest to most complicated. If you remember, our naive approach of extending our pairwise sequence alignment algorithm into n dimensions is intractable computationally, and so we need to apply some more imaginative and creative methods. So to start, we're going to talk first about an approach called the SPmin approach. And it looks something like this. For the SPmin approach, we start with some number of sequences greater than 2. We calculate all the pairwise alignments and we score them. And the scoring mechanism can depend on the individual. But the important part is that we generate a score for every pairwise alignment, every alignment of 2 sequences in this entire set of n. We'll talk about that in more detail in a second. And then we calculate what's called the sum of pairs score. We try to optimize that sum. Okay, so how does it work in detail? First, we calculate all the optimal pairwise alignments. As I said, remember there can often be more than one optimal score. We want the maximum alignment score or minimum distance score, depending on our rubric. Oftentimes, we can't tell the difference between multiple alignments. They're all equally good. So this will often lead to more than one optimal pairwise alignment. If you look at the small example on the right side of this slide, you can see that we have 3 sequences here for simplicity's sake. They're aligned slightly differently. If you look at the top 2 sequences in the top frame here, those same sequences are also aligned in the bottom frame here slightly differently. The score assigned to those 2 alignments is the same. Since we can't tell the difference between them, we have to treat each of them equally. Same thing goes for the bottom 2 sequences here. Those scores are the same even though the alignments are different. We assemble all of those pairwise alignments into a multiple sequence alignment similar to these 2 possible multiple sequence alignments we have here. And then we sum over all of the pairwise scores. So in addition to aligning sequence 1 and sequence 2 and sequence 3, we also have aligned sequence 1 with sequence 3 and derived a score from that. Those scores for alignments 1 to 3 are shown out here. So even though the 2 sub-alignments in this little grid are scored the same, top and bottom example, the 1 to 3 alignment is scored differently. We sum all those up. This gets a score of 14. This gets a score of 16. This would be our choice of alignments because that score is lower. Okay? In this particular case, a low score means a good score, so something akin to our edit distance here. Okay, how do we calculate pairwise alignments? How do we know how effective or efficient our approach is, our SPmin approach? The basis for calculating the efficiency of this approach is knowing how many pairwise alignments we need to calculate. How many possible pairwise alignments? This is something called the binomial coefficient, we have a set of n things, in this case n sequences. We are choosing any 2 from that set of n. So this is the binomial coefficient. It's read as n choose 2. And it looks like this. It's an n, that's the size of the set, over 2. It looks a little like a division, but there's no division bar inside parentheses. This has a particular value. We can calculate that value. Here it is in its generic sense, n choose k. Choose k, again, the binomial coefficient. You can find lots of information about this on the internet if you want to learn more about it. We are concerned with calculating this, given that we know the number of sequences. In order to calculate it, we need to use what are called factorials. We've covered factorials if you've taken any kind of math above algebra. They look like this. N with an exclamation point is read n factorial. And so to calculate n choose k, we simply use this formula here, n factorial divided by n minus k factorial times k factorial. This will give us the number of possible subsets of size k that exist in a total set of n. So in this case, n choose 2, it will give us the number of pairwise alignments that can be formed from our n sequences. Okay, drawbacks to the SPmin approach. We don't see SPmin widely available anymore. We've moved on to more efficient algorithms. One of the main drawbacks is there's no real efficient solution. This is what is called an NP-complete algorithm. There is no known solution better than polynomial. The second major drawback is it's not always possible to combine optimal pairwise alignments. Sometimes by aligning 2 sequences optimally, you are forced to align a third sequence with a very much worse score. It has a very slow running time, order m to the n. Just as a refresher, what does running time mean? That big O notation we talked about before spring break. Big O gives the upper bound on the running time of an algorithm. Remember, that's the worst case scenario for an algorithm. That's how we determine efficiency. It's cheating to take the best case. So we take what's the worst possible case for an algorithm and determine that as the upper bound, or the big O. It's based on the total number of operations, and it's written as a function of the input size. So if you look again, this is order m to the n, the SPmin approach. That's the worst possible approach in our big O grid. That's order n to the n exponential. What does that mean? That means that as you increase the number of sequences in your input set using the SPmin algorithm, the time it takes to complete that algorithm, to run that algorithm, is going to increase exponentially. Okay, that's the SPmin approach. As I said, we don't see it around very often. We're going to talk more in the next few lecture sets about more applicable, more modern algorithms for calculating multiple sequence alignments. Before we do that, though, there's a new activity up on eCampus, activity 16, where we play around with a little bit of factorial fun in Excel. So for this activity, you need to have Excel. If you don't have a copy of Excel handy, please send me an email. If you do, simply open a new workbook and follow along with the video called Factorial Fun. That will be in the YouTube playlist Excel Basics. I'll provide that link on eCampus with the other links for this course. Your goal, which you should be able to accomplish following the video, is to generate a graph that shows the increase in n versus n factorial as we go between 1 and 12. Okay, that video should only be about 10-12 minutes long. When you're done, submit your final answers as activity 16. You can either submit your Excel file with the graph in it, or you can just take a screenshot of the graph and submit that. Okay, thank you, and I'll see you next time.